Hello.
Yes, ma'am. Yes, ma'am.
Okay,
Yes, ma'am.
fine. Okay, so now let me present my screen. So is the screen visible?
Yes, ma'am.
Okay. So good evening, all of you. This is week 7 of live tutorial session on fundamentals of electronic materials and devices. So for the past 6 weeks, we have been solving problems that are related to your assignments and that are similar to the ones you can expect in your upcoming examinations. So we had been solving such questions, and in case anybody has doubts from previous sessions, please do ask immediately because since your exam is approaching. So without any delay, so details about me, like most of you might be knowing, I'm Santra Krishna. I'm a PMR of Scholar at IIT Madras, and this is the email ID that you can write to me if you have any additional doubts or queries. So without delay, we can go to today's questions. So the first question is, consider the N-type silicon sample with 10 power 15 donors. The temperature is 300 Kelvin and intrinsic, sorry, this is not, no, like this question I'll project later. So we'll start from here. Yeah. So the total region in a solar cell from which current is generated includes, like you can see four options: depletion width and minority carrier diffusion length in P region, depletion width and minority carrier diffusion region in N region, depletion width and minority diffusion lengths in P and N region, and only depletion width. So out of these four options, you have to find out the region in a solar cell from which current is generated. So you, everybody, like three of you, please take sufficient time and then come up with your answers. I don't know if this will be our last session, so I am combining questions from week 8 and week 7. So the previous questions that I initially showed are from week 7 and this is from week 8. So please take your time and please tell me your answer with an explanation. Somebody joined, I think. Yeah. Okay. So this is the first question. So the total region in a solar cell from which current is generated. So we can say that in a solar cell, we will be creating electron hole pairs, and due to the separation of these electron hole pairs, a current will be generated. So what is the region that is important with respect to this current generation? So can anybody tell me the answer and why?
Option C, ma'am.
Yeah, and can you come up with an explanation for that?
Yes, ma'am. Actually, in the depletion region, the whatever the electron and hole pair created by the light, so that the electron and hole pair will recombine and it gives the current. Same with happen in the P and N junction regions also, because there also, I mean, minority carriers will be there, so that will be recombined and gives the current, ma'am. That is the reason the current generated including the P region, N region, and the depletion region also.
Yes. So that is the correct explanation. So basically, once more I'll tell, in a solar cell, what happens is that electron hole pairs will be created inside the depletion width and they'll be separated and recombined in the external circuit. That is when current will be generated as the output, as well as minority carriers, they will be having a particular diffusion length before they die down in the P and N region, and that is also responsible for the current generation. So so basically the minority diffusion length is the average length that these carriers will travel before they get recombined. So is this answer clear to all of you? Somebody unmuted? So written explanation is shown here. For those who have any doubts, you can read that. Basically, electron hole pairs will be generated throughout the solar cell when irradiated. However, only some of them will contribute to the current. That is which ones are generated within the depletion region and within the minority carrier diffusion length. So the total width that contributes to the solar cell current will be basically the depletion width, that is WD plus LE plus LH, which are the diffusion lengths for electrons and holes respectively. So is it clear for all of you?
Yes, ma'am.
Okay. So this is the next question. Light of wavelength 550 nanometer and intensity 1 milliwatt is incident on a surface. Convert this into the number of photons per second and give your answer in units of seconds inverse. So everyone please try to work out this problem. Take a few minutes and then please tell me your answers. I want all of you to start working out, because even though if you have solved this problem previously, then also please try to solve and try to improve upon your speed so that it will be beneficial for you during the examination. So, have you started solving, and has anybody got the answer yet? Am I audible to you?
Yes, ma'am.
Okay, yeah. So then please solve and let me know. Wavelength is given, intensity of light is given. You have to find out n. What is the relationship between lambda, intensity, and n? That is the question. So the hint is that first you have to convert the wavelength into energy and then connect energy with intensity to get the number of photons.
Ma'am, it is 2.76 into 10 to the power of 15, but it's B.
You can approximate it to be 3 into 10 power 15.
Yes, ma'am.
Like whatever is in case the exact answer is not there in your option, you can approximate it as 3 into 10 power 15.
Okay, ma'am.
Yeah. So basically, energy is hc by lambda, right? And we know hc is 1240. So then E will be 1240 by lambda. That is the 550 that is given to us. And when you calculate this, you will get the value as 2.25454. So then intensity I is equal to LE by AT, where A is the area and T is the time. Suppose since nothing is mentioned about area, we will be considering it as per unit area, and also it is told that we have to calculate per second. So AT, the value of AT we can substitute as 1, which will give us I is equal to N into E. So here we already know E in electron volts and we have the intensity as 1 milliwatt. Distance, and now we have to know that both watt and electron volt are different units, right? So what is respect to joule? So we have to convert this electron volt also into joules. So when you convert, we have 0.001 by 2.25454, and we are converting it into electron volts by multiplying with 1.062 into 10 power minus 90. So approximately we will get the answer as 3 into 10 power 15. So is it clear to all of you?
Okay.
Yeah, so in case you have any doubts here, please do ask. So I hope nobody has any doubts. Since nobody is asking, then we can move on to the next question. So the quantum efficiency of a photodetector is defined as the number of carriers generated per photon. So how do you achieve a high quantum efficiency in a homojunction based spin photodiode? By making the width of intrinsic region much lower than penetration depth, by making width of P and N region larger than width of intrinsic region, by making width of intrinsic region much larger than penetration depth of wavelength, by applying a forward bias voltage to the photodiode. So please take a few minutes to think and then please come up with an answer. So basically quantum efficiency is such that suppose we are irradiating the solar cell with a given photon or say an array of photons, then electron hole pairs or carriers will be generated. So the question is that how do you increase this carrier generation? So what can we do to increase the carrier generation? It's actually PN photodiode. It's not pin photodiode. That's a printing mistake. So how do you increase the quantum efficiency? Means how do you increase the number of carriers in that PN photodiode?
Option C, madam.
Okay, by making the width of the intrinsic region much larger than penetration depth of the wavelength. Yes. So what is the explanation?
Ma'am, we make N and P region so small that light is incident on the intrinsic region, and the electron hole pairs generated in the intrinsic region then separated on the either side by reverse biasing the photodiode.
Yeah,
So much larger intrinsic region gives more electron hole pairs,
generation. Yeah.
and it helps us to separate also.
Yes. So basically the thing is that so when we are joining a PN photodiode, what happens? So intrinsic region basically is equivalent to what we say as the depletion region, right? So when more photons, when a particular amount of photon is incident, as the width of this intrinsic region goes larger and larger, we have a larger area across which electron hole pairs will be generated. Also, the penetration depth has to be reduced. Penetration depth means that whenever the photon is incident, it should be in such a way that the incident photon should not be lost by traveling or traversing through the thickness of the photodiode. So for a high quantum efficiency of a PN photodiode, the product of absorption coefficient in intrinsic region and the width of the intrinsic region should be much greater than 1. So that is a technical explanation that we can give. So which means that the width of the depletion region must be much higher than the penetration depth of wavelength. Therefore, the answer is option C. So basically, you can think of the intrinsic region, you can replace the word actually with the depletion width. So from that it is clear. We in the previous question we already learned that what only the electron hole pairs that are generated in the depletion width and the diffusion length are useful in photodiodes, right? So solar cell is also a photodiode basically. So what happens? So therefore, by making the width of the intrinsic region much larger than the penetration depth of the wavelength, we can increase the quantum efficiency of a photodetector. So is it clear to all of you?
Yes, ma'am.
Yeah. So next is it an S? Is a direct band gap semiconductor with a band gap equal to 3.9 electron volt. Assuming an ideal crystal with no trap state, that is what is meant by an ideal crystal. The portion of the electromagnetic spectrum where the emission lies is dash. Direct band gap semiconductor meaning that recombination would significantly lead only to the generation of photons, right? That is why we are asking where does the emission lie. So based on the band gap, you have to calculate the energy value, and based on the energy values, we will get the wavelength, right? So based on that wavelength, you will be able to say where the emission lies.
Is it UV?
Yeah. So what is the value that you got?
10 raised to minus 19 power.
Sorry, for what was that? Like we need to get the lambda value, right? Band gap is given to us, that is 3.9 electron volt. So
Uh,
yeah,
380 nanometers, ma'am.
yes. So when we are
Which
doing
is
using the Planck's law, when we are using, we have hc by lambda. So lambda is equal to 1240 by E. So this E value is given to you 3.9 electron volt. When you are substituting, you get this 317.94 nanometers at approximately 380 nanometers. So where does this 318 lie? So UV region is basically from 100 to 400, and in that also it is divided as UVA, UVB and UVC from 315 to 400, 280 to 315 and 100 to 280. So this 318 lies in this UVA region. So that is why the emission would be in the UV region. So is it clear?
Yes, ma'am.
Yeah. Okay. So next, just choose the correct statement or statements. So the intensity of solar radiation at an air mass number AM2 is higher than AM1. AM2 is lower than AM1. AM0 is lower than AM1 and AM2 is lower than AM0.
actually they haven't taught anything about air mass, madam.
Okay, like in solar cell, they have not taught like solar cell efficiency is calculated at a particular AN number. Those kinds of things have they taught?
No, 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 madam. No, they haven't taught in the video. Actually, I've seen complete video.
Okay. So then I think you'll have to see the explain. So basically air mass number is what is the secant of the angle between the sun and the zenith. So basically, and I think I can get you an image of air mass number. I thought it was taught in class already. See, basically this is the diagram that we can see. So here we can say that the sun would be at an angle of 0, and as the sun moves with respect to the horizon, that is how we define an air mass number. So then we can see that air mass number is the secant of the angle between the sun and the zenith. Air mass 0 represents the solar spectrum that is outside the Earth's atmosphere, and AM1 is when the angle is 0. That is, sun is at the zenith as an intensity of 925 kilowatts per meter square, and AM2 is such that when it is at 60 degrees and its intensity is comparatively less. So what happens is that when we are seeing the spectrum outside the Earth's atmosphere, that is when we call AM0. When the sun is exactly at this point, that is exactly straight with respect to the horizon, the value of theta will be 0. That is what is AM1, and it has an intensity of 0.925 kilowatts per meter square. And when it moves to an angle of 60, suppose this is the angle 60, the intensity will be reducing respectively. So that is how we Like usually in case of solar cells, what we do is that we measure the efficiency by providing a particular AM value. It will be usually measured at AM1. So where we will get maximum efficiency. So then here we can see that what would be the answer. Now that we know that AM0 is outside the atmosphere and it will be much more. AM1 has more intensity than AM2. So which of these two options would be correct in that case? So as the AM value increases, the intensity will be lower. Now can you tell me?
Option D, ma'am.
Yeah,
Option
option
D, ma'am.
B and one more is there.
Option B.
Yeah, option D and option B will be the answer. That is the intensity of solar radiation at 2 will be less than that at 1, and at 2 it also will be less than that at 0. Because here we are getting approximately only 0.691 kilowatts per meter square. So is that clear?
Yes, ma'am.
So this is the next question. Which of the following statements is true regarding solid state lasers? Active lasing semiconductor should be an indirect band gap semiconductor. Lasing is mainly due to spontaneous emission. It requires total internal reflection to increase the intensity. Homojunction lasers are more efficient than heterojunction lasers.
Straight C, option C, ma'am.
Yeah, so why can you give me an explanation of why?
Because as we want to increase the intensity of the laser, one thing is population inversion and second thing
Yes,
is total internal reflection
yes,
and stimulated emission
yes. Like
or to
spontaneous
get the
emission is out
coherence.
of question. Yes. Yeah. So is it clear? So in case of solid state lasers, like one option is like we know it's simulated emission. So this option is not correct at all. And lasers will require total internal deflection to increase its intensity. Hello?
Yes, madam.
Yeah. So is it clear to all of you?
Yes, ma'am.
Yeah. So next is the absorption coefficient of a semiconductor is given as 2 into 10 power 5. The thickness of the semiconductor is 100 nanometers, and if I0 is the intensity of light, incident light, what is the intensity of the light coming out of the semiconductor, and we have to choose the nearest value. Absorption coefficient is given, thickness is given, we have to find the relationship between I and I0. So which law would you use here? There's a name for this law that we'll be using for this question.
Beer-Lambert law, madam.
Yes, you can use Beer-Lambert's law.
Option 1, I naught.
I don't think so. Like, what is the relations that you used?
I is equal to I naught exponential power minus alpha into t.
Okay, and did you convert the units? Absorption coefficient is in centimeter inverse and thickness is in nanometers.
Yes, ma'am. I converted into 10 raised to 2 meter inverse, and here 100 nanometer, meter get cancelled.
Ma'am, I also got the I naught only, ma'am.
Okay, then I need to work out with inches. Give me a minute. Basically, you get point 0.1, right?
Is it the option?
Point.
Hello?
Ma'am, I got 0.99, ma'am, like that.
Yeah, so it will be point 0.1, right? So basically 0.14 might not be exact, but 1.1 and 1 would be very different, right? So if you are telling that if it is I0, then it means I is equal to I0, right? I is equal to
Ma'am,
I,
I got point 136
yeah, point,
value.
yeah. So that would be
Point
I,
136.
yeah, so it would be 0.136, right? So it won't be I0 exactly. It would be option C, 0.14.
Yes, ma'am.
Yeah, so where did you go wrong?
Uh, like I don't know, madam, where it went wrong.
Yeah, because if you say,
Actually, I did second time.
uh-huh,
Second time I got 0.135.
yeah, because even if you don't get 0.99 also, if you get, you can approximate it as 0.1. See, if you say 0.1, if A's answer, how it would be, I is equal to I0, means whatever intensity goes in is coming back. But if you are getting 0.99 also, it means that whatever intensity is going, only 0.99 of it is coming back, right?
Yes, ma'am.
Yeah. So why is that initially we got zero point 0.9? Does anybody know? Like when I calculated initially, I got that 0.136 thing, but I didn't understand why you got 0.99.
Ma'am, it is just this absorption coefficient multiplied by the thickness. That's
Yeah,
it, right,
that's it.
ma'am?
Yeah,
And the exponential of that value gives the like that. I got the 0.99, ma'am.
yeah.
Uh,
Then
I converted that nanometers into meters and centimeters also into meters. Ah, yeah, ma'am, I got it. In the conversion of centimeter inverse, it was there. So,
okay,
okay.
fine, fine, fine. Yeah. So is it clear to all of you then?
Yes, ma'am.
Yeah. So next is the open circuit voltage of a PN junction solar cell is 0.45 volt when the photocurrent is 50 milliamps per centimeter square. What is the open circuit voltage when the photocurrent is increased to 500? Take the temperature to be 300 Kelvin. All the other device parameters remaining same. And you have to give your answer in volts.
Is it option D?
Yeah, what about other people? Are you getting the same answer?
Madam, I need time. I'm sorry.
Yeah, yeah, you can solve. You can solve.
I will go with option D, madam.
Okay, so both of you got 0.51. So is this the equation that you used? KBT by E ln IPH by ISO?
Yes, madam.
Yeah. So initially it's given that IPH is the photocurrent is equal to 50 and EOC is equal to 45, and we can find ISO using that, and it is as 1.4 into 10 power 9. So once you substitute the new value, you will get 0.51 volt. So is this clear?
Yes, madam.
Yeah. So next question is, which of the following statement is true regarding light interaction with an indirect band gap semiconductor? So light of energy less than band gap gets absorbed, forming electron hole pairs. Recombination leads to light emission. Recombination leads to heat generation. It is possible to reduce the emitted wavelength by creating deep trap states in the semiconductor.
Option C, ma'am.
Option C.
Yeah, so recombination of excited carriers primarily leads to heat generation. So in case of direct band gap, it would be both heat and light generation. So that is the only difference. So the next question. Choose the correct statements regarding a solar cell made up of silicon. The band gap is given as 1.1 electron volt. So wavelength above 1.1 microns are not absorbed since energy is lower than the band gap. For wavelengths much smaller than 1.1, absorption coefficient is very high and electron hole pairs are generated near the surface and get trapped by surface defects. Wavelengths above 1.1 microns are not absorbed since the energy is higher than band gap. For wavelengths much smaller, the absorption coefficient is very low and electron hole pairs are generated in the bulk of the P region.
Option B and D, ma'am.
B and D. Okay, what about the other person? Anybody else?
Madam, I need 1 minute.
Yeah, yeah.
B and C option.
Yeah. Okay. So B and C, one person told. B and D, one person told. Anybody else? So it's basically A and B.
Yeah, madam, because the statement with A is wavelength above 1.1 are not observed. That is true. Actually, since
Yes.
EG becomes less as lambda
This
increases.
is yes. And for B part, what happens is that for smaller wavelengths, absorption coefficient will be very high. And what happens because of the surface defects, it will be trapped. Recombination will happen, right? C is not correct because see, whenever we are supplying an see what suppose we have an energy band here, the energy gap is 1.1 electron volt. Whenever we are giving 1.1 electron volt or more, excitation will happen. So lambda and here inversely proportional. So 1.1, 1.2, 1.3 and so on. It will get absorbed and subsequently what happens? All wavelengths that are less will be absorbed. So wavelengths above will not be absorbed because the energy is lower than the band gap. So that is one option. And then D is what happens? So for wavelengths that are much smaller than 1.1, suppose it's very, very small. So say, for example, 1240 divided by 1.1 will give us something like 1127. So basically in a silicon solar cell, everything that is less than 1127 will be absorbed. That is why we can cover the entire spectrum. Suppose we are going for very, very small wavelengths, say like 100 or 200. In that region, what happens? The absorption coefficient will be very high and hence the electron hole pairs will be generated near the surface, and due to the presence of trap states, what will happen? Recombination will occur. So the answer will be A and B. So is this clear to all of you?
Yes, ma'am.
Yeah. So
Yes, ma'am.
next is consider a photodiode formed between PTSI and SI. What is the maximum wavelength of light for which excitation is due to band absorption is in SI? So the band gap of silicon is 1.12 electron volts.
Option A, ma'am.
Anybody else?
Option A.
Okay, so two people told A. Anybody else? Yeah, so the answer is option A. So basically for 1.12 electron volt, we have approximately 1100 nanometers, right? Therefore, for all wavelengths less than 0, excitation will be due to that in silicon. So they have asked only due to band absorption silicon. That is why we are calculating only respect to 112. So in the photodiode, there is a region of silicon alone. And in that silicon region, what will be the maximum wavelength out of these four options that can be absorbed? That is 1100. So is it clear to all of you?
Yes, ma'am.
Yeah. So next is consider an N-type silicon with a dopant concentration of 5 into 10 power 50. It is illuminated with light that creates 10 power 21 electron hole pairs per centimeter cube. The minority carrier lifetime is 50 nanoseconds, and at steady state, what is the ratio of electron to hole concentration in the semiconductor? Ni, or intrinsic carrier concentration, is 10 power 10 and temperature is 300 Kelvin.
10 raised to minus 2, madam.
Yeah. So other people also, can you start working out and tell me?
Actually, it was there in
Assignments, yes.
assignment 7.
Yeah. I want all of you to get 10 power minus 2 list. So everyone take your time, work out and then tell me.
Ma'am, it is 10 power minus 2, ma'am.
Yeah.
Madam, I have a doubt in 7th problem
7 in
of
assignment?
assignment 7.
Okay, 7.
7.
Okay, so once we discuss this, we can see.
Okay.
So is everyone getting 10 power minus 2?
Yes, ma'am.
Yes, ma'am.
Okay. So ND is given as 5 into 10 power 15, and minority carrier concentration or the electron hole pairs that are generated is 10 power 21 into 50 into 10 power minus 9. So basically it's 5 into 10 power 30, and hence the new electron concentration would be their sum, that is 5 into 10 power 50, and hole concentration is Ni square by Nd plus delta T, that is 5 into 10 power 30, and on dividing these two values we will get 10 power minus 2. So is it the same way that you all got?
Yes, ma'am.
Yeah. So next is at steady state illumination, 10 power 16 electron hole pairs are created in an intrinsic silicon sample. Electron hole mobilities are given, the intrinsic carrier concentration is given, and you have to find out the electrical conductivity at illumination. And answers should be in ohm inverse, centimeter inverse. This also I think was part of the assignment.
Yes, ma'am. And the answer turned out to be 2.9.
Sorry?
2.9, ma'am.
Yeah. So people who have not like worked this out, please do work this out and find if you are also getting 2.9.
I got it as 3, man.
Yeah, like maybe some units or something would be different, but nonetheless, it's near to 2.9, right?
Yes.
Yeah. So basically, you have to use this equation. Sigma is equal to Ni mu e plus mu h, and upon when light is incident, what happens? Ni will be replaced by 10 power 16. And when we substitute 10 power 16, we'll get 2.9 ohm inverse centimeter inverse. So next is, if light of energy E greater than Eg is incident on a semiconductor, electrons are excited above the conduction band edge, and the excess energy will be released as heat. The process by which this heat energy is released is known as, it's a very simple question, I think.
Thermalization.
Yeah. So everyone is okay with the answer, thermalization?
Yes, ma'am.
Yes.
Yeah. So next is, electroluminescence is a phenomenon of light emission when electronic excitation is created by ionizing radiation. It is created by electric field, electron beam, or by incident light.
Option
Option
B.
D, ma'am.
Sorry, what?
Option B. B.
Oh,
Option D, ma'am.
Option B.
B. Yeah. So
B. B.
electroluminescence is when there is light emission because excitation takes place due to an electric field. So the answer is option B. Yeah. So next is, a certain PN junction LED has an emission wavelength of 400. What is the line width at 300 Kelvin and 77 Kelvin? So please do work out and let me know. Somebody joined right now.
Option B, ma'am.
Okay, for others, yeah, please take your time.
Option A, madam.
Option A. Okay, another person got option B, right?
Ma'am, it's actually I got 5.6, so I approximated downside instead of upper side. So
Like whenever it's
like that,
greater
I
than 0.5, you should approximate on the upper side. 5 or greater means you can approximate on the upper side. If it's less than 0.5, you have to approximate on the lower side.
okay. And then option A, ma'am.
Yeah. Others? Everybody got option A?
Option A, madam.
So is this the equation that you use? Delta lambda is equal to 1.8 kV G lambda square by Hc?
Yes.
Yeah. So upon substituting whatever is given to us, for in the first case we'll get delta lambda is 6 nanometers, and in the second case we'll get delta lambda is 1.5 nanometers. So I hope it's clear to all of you, like emission wavelength is 400 nanometer, temperature is given, Boltzmann's constant we know, and Planck's constant also we know, speed of light also is known. Like most are constant except for temperature, and when you change the temperature with respect to the delta lambda value will change. That's all. It's direct substitution question. So I hope it's clear for all of you. So next is the internal quantum efficiency
Yes, ma'am.
of an LED is 90% and the external quantum efficiency is 85%. What is the optical efficiency of the system?
Option D, madam.
Okay, others?
0.94.
Sorry, 0.9135 or 4?
0.94.
0.94. Okay. So two people have got 0.94. What about others? Yeah, so basically this is the equation. NEXT is equal to NIN into NOP. Here NOP or the optical efficiency is given, is asked, and internal and external is asked to us, and on substituting we will get 0.94. So option D is the right answer. So is it clear to all of you?
Yes, ma'am.
Yeah. So next is arrange the following semiconductors in the order of increasing wavelength of emitted light during recombination. They are all direct band gap semiconductors. So here the same logic applies. Whatever would be the band gap, based on the band gap, lambda would have an inverse relation with them.
Option B, ma'am.
Okay, others like yeah, 1% told option B.
I will go with option A, madam.
Okay. So basically, with respect to energy, when we are calculating for gallium arsenide is 1.42, for cadmium sulfide it is selenide, sorry, it is 1.74, and for zinc oxide it is 3.37. So energy has an, they are asked in the increasing order of wavelength, right? So energy increasing order would be GAS, CDSE and ZNO. So here we have to arrange sum of increasing wavelength. So increasing wavelength would mean that the opposite. Zinc oxide, cadmium selenide and GAS. So option A will be the answer. So whatever increasing order energy has, lambda will follow the opposite. So option A is the right answer. So is it clear to all of you? They have
Yes,
asked
ma'am.
in wavelength.
Yes, ma'am.
Yeah. So in case of energy is asked, you can go with option B. That would be correct. But here it is asked with respect to wavelength. And since they have an inverse relation from this equation, we have to write the reverse order. So next is choose the correct statements. Incident optical radiation causes transition of electrons from excited state to ground state, leading to simulated emission. Emitted light is in phase with incident. For efficient lasing action, spontaneous emission must be suppressed and simulated must be promoted. Main criterion for laser action is population inversion. There must be greater number of occupied states than ground states. For the rate of simulated emission to be greater than the rate of absorption, population in the ground state must be more than population in the excited state. So out of this, a few statements are correct and you have to choose the right ones.
B and C.
Okay, others?
A and C, ma'am.
Okay. Actually, it is A, B, and C. One person told B and C, one person told A and C. Actually, all three options are correct. Basically, whenever there is incidence, what happen, excitations will happen, and after excitation there is a transition from the excited state to ground state, leading to a simulated emission. And in a laser, this emitted light will be in phase with the incident light. For efficient lasing action, simulated emission is preferred and promoted, and spontaneous should be suppressed. Also, we already know that total internal reflection and population inversion are two main criterion for laser action. Therefore, option A, B and C are correct. So is it clear?
Yes, madam.
Yeah. So next is in tandem solar cells, why is the cell with a smaller band gap at the interior, while the cell with higher band gap is closer to the illuminating surface? So shorter wavelengths are absorbed by the outer cell and longer by the inner ones. Larger the wavelength region gets used to improve efficiency of the solar cell and to reduce efficiency of the solar cell.
A and C, madam.
Okay, others?
A and C, ma'am.
Yeah. So basically it's A and C. Shorter wavelength would mean that more energy values, right? Lesser band gap, larger band gap values on the outer cell, and whatever further goes inside will be absorbed by the inner cell. And due to all the range of wavelengths being absorbed, the overall efficiency of the solar cell will increase. That is why we use tandem solar cells in the first place. So is it correct and clear to all of you?
Yes, ma'am.
Yeah, usually what happens is that whatever is absorbed in one region and to the left is just transmitted, it will be lost. So that these longer wavelengths are also captured, we will create a second junction such that the lower wavelengths are allowed to pass through and get absorbed by the inner cell. So that is the case here. So these are the questions for today. I hope it was clear to all of you. And in case you have any
Yes,
additional
madam.
questions and queries, please do post in the discussion forum or email me. Now we'll go to the assignment 7 that you were asking.
Ma'am.
Assignment 7, question 7, right? Consider a wide band gap semiconductor with a band gap of 3.4. Photons of wavelength 300 nanometer are incident. Photon flux is given. Every photon is converted. Total heat generated due to thermalization. So what is your doubt?
Madam, I got the answer as 6.6.
Okay, 6.6 into 10 power minus 19 joules, right?
Minus 3 watt centimeter minus.
Okay, so why is that Hc by lambda? So basically E is 1240 divided by 300. So 4.13. For initial part E value, how much did you get? 4.13 electron volt, right?
1 4 electron volt.
Okay, and total heat generated due to thermalization is such that band gap is given. So 4.14 minus 3.4 you have to calculate and convert them into joules into number of carriers, right? 4.14 minus,
Minus 3.4, madam.
yeah,
Why?
because here it is told that the band gap is 3.4, right? And
Yes, ma'am.
energy of the photons will be such, like, see, whatever is required for excitation out of 4, suppose we have these 300 nanometer photons are there with us, right? So they have a particular
Yes,
energy.
ma'am.
Out of the total
Yes, ma'am.
energy, only whatever is required for the band gap will be utilized. Whatever is left behind, even if it gets excited, they will return to the ground state. That is lost. Here they are asking due to thermalization alone, right?
Yes, ma'am.
Yeah, that is why we subtract 4.1.
1 second. Can I solve it, madam?
Yeah, yeah, you
And
can
see.
solve. You can solve.
Same mistake I also done, ma'am. I didn't subtracted that 3.4, so I also chosen the 6.6.
Okay, fine, fine. So here the thing is that suppose our material has a particular band gap, only that much is required for excitation to happen. Whatever extra we are giving will be lost due to thermalization. So here they are asking only that part due to thermalization.
Yes, ma'am. Got it.
Madam, then how to solve, madam?
So basically E value you got as 1.14, right? And that 1.14 you multiplied and converted it into joules and then multiplied with 10 power 16. Here instead of directly multiplying 4.14 you have to subtract, that is 4.14 minus 3.4 into 1.6 into 10 power minus 19 into 10 power 16. So you will get somewhere like 1.184 into 10 power minus 3 watt centimeter per minus 2. So that 10 power minus 3 you can do as milliwatts. Here they have asked in
Got it, got it, got
yeah,
it.
yeah, that's all.
Madam, another question.
Yeah. Question number?
Non-graded assignment, madam.
Non-graded assignment, which week?
7th week, ma'am. Non-graded assignment. Second one.
Okay, let me see. Seventh week, non-graded assignment.
Second one.
Okay, consider N-type silicon sample with 10 power 15, that question.
Yes, ma'am.
Yeah. So, actually I had made that question for today. So, does anybody else know the answer to this question? Yeah, this question. This is the question, right? If
Yes,
anybody
ma'am.
else who has,
Uh,
yeah.
like, no, I can't imagine, madam. They are like saying that what will be the lifetime, something like that. They just made up confused.
Yeah. Did anybody else get this answer?
Ma'am, can you share the screen?
Okay, yeah, I'll share this. In case it's wrong, I'll ask if there is anything wrong with the question. Let me present my screen. Okay. Is this visible to all of you now? Yeah. N-type silicon.
Yes, ma'am.
Yeah. So this question. N-type silicon sample with 10 power 15 donors. Temperature is 300. Intrinsic area concentration is given. So it is illuminated with light such that steady state it is 10 power 14 minority carriers. When the light is turned off, how long will it take for the whole concentration to reach equilibrium value before the light was turned on? I have not solved this question.
Like they have me confused, madam. They said so many things that it is not going into head.
Okay, initial part we can say, right? It is N-type, ND is given to us, temperature is there, Ni is there. Then when we are illuminating, means that minority delta P values are given to us 10 power 14. Delta P is equal to delta N is equal to 10 power 14 value we have.
Yes, ma'am.
Yeah, and the minority carrier lifetime is also given to us. Now we have to find out if the light is turned off, how long will it take for the minority carrier concentration to reach equilibrium value? Yeah, so has anybody solved this question?
I didn't solve it, madam. I didn't
Okay.
get it how to solve.
Others?
No, ma'am, I also didn't.
Okay, I have also not solved it yet. So I will look into this question and I'll post the answer. Will that be okay? I have to say my notes.
Okay, madam.
Yeah. So this question I'd ask.
Madam, you told you will take classes regarding
Yeah,
FET and
yeah,
MOSFET,
yeah. So
madam.
the thing is that since your examinations are 26th, right? 25th or 26th for this course, when is this?
26th,
6th.
madam.
Yeah. So they have asked me initially to complete like weekly courses, and if possible, we can request for a session this week itself before your exam. Like when,
Yeah, madam.
yeah,
Like MOSFETs are like very much confusing.
yeah. So can you both just give your mail IDs in the chat box so that I can forward this answer to both of you? The ones we just know saw, right?
Okay,
Yeah.
madam.
Yeah, both of you just post it. So I also need to look into my notes. So yeah, okay, both of you. Thank you so much. So yeah, I'll solve this and I'll send the answer to you. Yeah,
Madam,
yeah. Tell me.
madam, in this week's assignment,
Okay.
non-graded assignment, the second one, madam.
Non-graded second one. Let me check. Open circuit voltage is given, photocurrent is given. What is the current density of solar cell operated? Okay.
Yes, madam. I didn't got how to solve it, madam.
Like equation for current density, do you remember?
Yes, ma'am. I calculated open circuit voltage first day. From that, I calculated short circuit ISO, short circuit current.
Okay.
Then from using ISO, after that, I don't know, madam, what I have to do. Yeah,
Hello?
yes, ma'am.
I'm checking 1 minute. Current density, basically you have to find JSC, right? You know VOC.
Yes, ma'am.
Okay.
Uh,
Current is given, current
but
density.
for GSC, I think we haven't discussed anything in our course, ma'am. We haven't calculated current density in the videos.
Okay. So that part you have not like it's not explained in the videos you're telling.
Yes, madam. But on the other hand, also about what are the properties that about Pearl, madam? About Pearl semiconductor,
Okay.
like why zigzag is there? Sir, like simply told that zigzag will be there and finished.
Okay. So I'll have to ask
That's-
that. Okay. I'll ask to the TA why like whether Pearl is important. Is it in the optional videos in the actual examination related videos?
Madam, they have posted that slide in summary video,
Okay. Yes,
but
JSC
they
VOC
just
now
said
whatever I think.
Pearl.
Yeah, Pearl.
They have just said that Pearl and there will be like zigzag. It will be there. They haven't mentioned zigzag also. They said some other word and they moved on.
Okay. So Pearl semiconductor
As
there is a
per
question also, right? Yeah.
uh, as per madam, like zigzag maybe like from my imagination, like zigzag maybe means if light falls means if it reflects means then it will go. If zigzag surface is there, then it will stay inside that only, and we
Yeah,
will get more
yeah,
efficient.
more efficient. More absorptions will take place in case we are putting any patterning on the surface.
Yes, madam.
Yeah, maybe that is what he meant. And this open circuit voltage question, I can, like, I have not solved. I think we can relate it only when we have fill factor, right? So from the given data, if you can calculate fill factor, means you will be able to solve, I think. You can think in that route, maybe. Like JSC, we have to find out. VOC, you can calculate. Then Vmax and Jmax, if we can get from whatever is given. Yeah, I think I need to solve this one also. I'll solve and send the answer for this one as well.
Okay, madam. I'm Anil, madam.
Yeah, yeah. Okay. Yeah, for Saujit.
Madam, another one question I have, madam.
Yeah.
Which of the following does not change with the dimension of the solar cell? They have asked this question in 14th one, madam.
Assignment.
8, madam.
Okay, 14th one. Still, let me see. Saujanya, were you able to solve this non-graded question that he just told?
Ma'am, that time I solved, but now I didn't remember, ma'am.
Okay, yeah, I
I have to check back.
okay, fine, fine. So 14th is which of the following does not change? Okay. So you don't like basically what is your doubt in 14th question?
Madam, I don't have any idea regarding this.
Like
What changes?
photo generated current can change, right? When we are changing the suppose dimension means you just imagine that you are changing the width of the depletion region. Then it would mean that whatever
Uh,
number of electron hole pair
Photo current will change.
change.
Then power output will also change,
Change,
madam.
yeah.
Then
So A and D are not in the option. Then a reverse
yes, madam.
saturation current will also depend on this recombination, right?
ID, ISO is equal to Ni square dV by.
See, like when I think,
Huh?
if I am correct, when we are changing the depletion width, it should be at an optimum value such that while traversing lot of recombination also should not happen, but sufficient electron hole pairs should also be generated. So I think A, B, and
Yes,
D
madam.
won't be an answer, and hence only option is open circuit voltage. So it is basically a ratio of photo generated current and reverse saturation current, right?
Yes, madam.
Yeah. So it is open circuit voltage.
Madam, even the reverse saturation current does not depend upon the dimensions, madam. Like it is equal to Ni square into E divided by dE by
Ni square
Le
into,
into
sorry,
Na.
like when you are seeing that equation, you should check whether any of these values in the equation are dependent on this dimension.
Like Ni are not dependent on how much we use, ma'am.
Yes,
Ni
yeah,
is constant if you
basically, yeah,
use
for the,
1 gram of silicon or
yeah,
100 gram.
for what are the other parameters for ID?
Other D is there, ma'am.
Okay,
Diffusion length,
okay, diffusion length
diffusion
will change,
coefficient.
right?
Diffusion length L is equal to square root of D into tau E.
Yeah, when we are manipulating width, I believe the diffusion length might also change.
Like I have doubt with these two, madam. Reverse saturation current and
Open
open
circuit
circuit voltage.
voltage. I think open circuit voltage would be the answer.
Madam, open circuit voltage depends on IPH, madam. Since photo generated current changes, VOC will also change.
Yeah, it will be ratio of photo generated and reverse saturation current, right? So when since,
Ah,
yeah,
yes, ma'am.
so since both are like in numerator and denominator, if the change is reflected, means that it would be independent, right?
Yes, madam.
Yeah.
They both will change.
Yes.
Yes, yes,
So like when one is changing or increasing or decreasing with the same way, another will also be changing. So and since they are a ratio,
yes, madam.
then overall open circuit voltage won't change.
Yes, madam. Yes, madam. Sure, sure, sure.
Yeah.
Madam, that if possible, please take a class on FET and
Yeah,
MOSFET, madam.
usually we have
And some
revision
more
sessions because
questions.
last time what happened was like there was a 1 month gap between when the course was ending and the examination was happening. So we got sufficient
Yes,
time to
ma'am.
plan for revision sessions and all. But now let me ask them. Yeah. That is
If
why,
possible,
yeah,
please, madam.
that is why actually I included week 8 also. Usually we should be getting one more week, right?
Yes, madam.
Yeah, so I'll ask them. Yeah, and those other two questions I'll solve and I'll post it to you.
Madam, like this week, seventh question.
Um,
Which of the following fair interpretation of quantum efficiency, madam?
Question number 7. Okay, which of the following is a fair? Okay, options are
Like I have doubt in first and second option, madam.
this
It is
current
from
generated
the
per watt. Okay, I think first would be the answer. Yeah, it is.
even I ticked it as correct, madam. Then my head is saying, yeah, current generated per watt of incident light is also correct because I have a efficiency eta is equal to IPH by E into HC divided by lambda into power output POP.
Okay, but basic equation for quantum efficiency would be IPH by E5, right?
Yes,
So
madam.
basically, IPH means what? The amount of like current indicator of number of electrons generated. That is current
Yes, madam.
generated.
Yes, madam.
Yeah, yeah,
Yes,
yeah.
yes, quantum as quantum efficiency. This is correct, madam. But NETA also have this one more equation, madam.
Current,
Hc by lambda into power output.
HC
If I
by
use that equation, that the second option will be like feels
HC
like
by
correct one.
lambda into power output. Is that quantum efficiency or some other efficiency? Like I don't.
It is quantum efficiency only, madam.
Okay, quantum efficiency. I basically remember only this equation, IPH by E5.
I even showed this equation, madam. That's why I got confused.
Okay.
Like both are looking like correct. After they say that, ma'am, neta is equal to IPH by E5,
Huh?
they continued and said that neta is equal to IPH by E into H nu by POT. OT is the optical power.
Okay.
Just after that, they have said like this.
It was mentioned in the class or
Class, madam. It was mentioned in the class.
okay. So can you send me like that part means what is the second equation that they sent into my mail ID? Can you just send?
Now only, madam.
Like after the class you can send.
Okay, madam.
Yeah. Because I think A would be the answer. Let me check if B is also correct.
Yes, madam.
Yeah.
That's it, madam. I got all other questions.
Okay. Yeah. So then I think we can end for today, and whatever doubts you ask, I can go through them once more and then be back with you.
Okay, ma'am. If we have any more doubts, means we can mail you,
Yeah,
ma'am.
yeah, you can mail.
Okay, ma'am.
Yeah,
Ma'am,
yeah, tell me.
ma'am, if we want to write this exam again, like not in the exact slot, is there any chance to remodify our exam like
No,
date?
slots you can remodify. Only what?
Not slots, ma'am. Date of
No, no,
examination.
that will be fixed everywhere, right?
Okay,
Yeah,
ma'am.
like
I mean, no exceptional like that.
no, no, nothing like that. Because all over India, people would be registering, and if and for like if there are exceptions again, they'll have to prepare question papers and all, right? Like it's like a centralized system, so there
Oh,
won't
okay,
be
ma'am.
any exceptions.
Okay, ma'am.
Yeah. Okay. So thank you both for joining and staying for so long. Others left. So whatever doubts you have, I'll work them through and then send it to you.
Okay.
Yeah.
Thank you so
Okay,
much,
ma'am.
ma'am.
Thank you.
Okay, ma'am. Thank you.
Thank you so much for joining. Yeah. Bye bye.
Bye, ma'am.
Yeah.
Bye, ma'am.